Hello, this is our narrated version of the last PowerPoint for Earth Science class. So this last topic is called Atmosphere and Weather, and don't pay attention to the chapter numbers that are on here. That's from a different textbook. I think for our current textbook, it's chapter 17, 18, and 19, I believe, something like that. Anyway, you guys are certainly capable of finding out what chapters this is covering. And some of this material may be presented in a slightly different way than what's in your book, but there's nothing wrong with that. It is the same material. All right, so atmosphere and weather. We will start with how the atmosphere is. You're going to need to know the difference between weather and climate, and I had a short snippet about this on the board in class last week. Remember that weather is over the short run, okay? It's constantly changing. The weather can be incredibly different from, in the morning when you head to class, and then in the evening when you're heading back home, it may be completely different. It may have warmed up by 15 degrees, and it may have gone from just a few cumulus clouds to perhaps a thunderstorm rolling in. Climate is over the long run. It's basically a long run aggregate of weather, and you're going to need to know the minimum number of years of weather data that is needed to be able to make any determinations about climate, and that answer is 30 years. We need at least 30 years of weather data to be able to say anything about climate. Do we have at least 30 years of weather data in the United States? And the answer is yes. We have many decades of weather data. And if you look at older countries, like say over in Europe, or the Asian countries or African countries, their weather data is probably going to go back even more decades than ours will. All right, you don't need to write any of this down, but let's say if you were to become a meteorologist, first of all, you'd have to transfer up to NC State to become a meteorologist, and let's say you're going to go work for the National Weather Service. These are the kind of things that you would be measuring constantly. Temperature, humidity, probably in the form of relative humidity, cloudiness, precipitation, air pressure, wind speed, and direction. Okay, what is our air made of? So, yes, you need to write these down if you were not in class to get written down what I had on the board. I'm going to want you to know the fixed gases in our atmosphere and the percentages of them. And this is likely to be a short answer question. Okay, so 78% of the air we breathe is nitrogen, and that should say N2, atmospheric nitrogen. Oxygen, O2, atmospheric oxygen, is important, but that's only 21% of the air we breathe. And then the other less than 1% is made up of argon and all other gases. Now, carbon dioxide. So we think of carbon dioxide as a fixed gas, but that's really only in the very short run. So what I have here on the slide is 0.039%, and honestly that really probably needs to be tweaked. Now they're saying more like 0.04%, and when I first started teaching at UNC Pembroke back in 2008, our carbon dioxide levels were 0.037%, so they are indeed increasing. And why do we care? Why do we keep an eye on carbon dioxide? I mean, look, the percentage is pretty small. Well, we have to keep an eye on it because it is a greenhouse gas. Okay, variable components of air. I had these written down on the board for anybody that made it to class this past week. They're going to include water vapor, aerosols, and ozone. So we'll begin with water vapor. It is the most important of all the variable components of air. Why? Because it is a source of condensation and precipitation, and we do need precipitation. No, we don't like it when we get too much, like in the form of our tropical storms and hurricanes bringing flooding, but we do need precipitation. Why else is water vapor important? Because it is a greenhouse gas. So it's absorbing energy from the Earth. We'll discuss this, how the troposphere is heated later in the PowerPoint, but it also, in the form of clouds, can deflect some of the incoming energy from the sun. So aerosols are another variable component of air. They are tiny solid and liquid particles. They're going to include all the things listed here: dust, smoke, soot, pollution particles, yes, water droplets, meaning condensation, volcanic ash, clay, pollen, sea salt. So the aerosols are important. For one thing, they're going to act as condensation nuclei. Now, ozone is our third variable component of air. And ozone is oxygen, but it's O3. Okay, so the atmospheric oxygen that we're breathing right now is O2. Ozone is different. Ozone is O3. And yes, sometimes and in some locations, we end up with ozone being produced in the troposphere where we live, and that's not a good thing. And that's part of what they refer to as photochemical smog. But in this semester, we're not going to have time to discuss tropospheric ozone. But if you enjoy this last unit, I will let you know that we do teach a class called Atmosphere and Weather. Or sorry, it's called Weather and Climate, and that's all that we discuss. So I teach it every fall, and Dr. Edgel teaches it every spring. So for this class, we're just going to focus on the ozone layer. Hopefully everybody's heard about the ozone layer. And where does it hang out? It hangs out in the stratosphere, which is the second layer up in our atmosphere. And it's important because it blocks, absorbs some of the harmful ultraviolet radiation coming from the sun. And back in the late 70s, early 80s, we discovered that there's a hole in the ozone layer. And then we quickly determined that it was the use of CFCs, chlorofluorocarbons, that were causing the hole in the ozone layer. So the United States and several other, industrialized countries, first world countries, we got together and we signed an agreement called the Montreal Protocol, and we phased out the use of CFCs. And the hole in the ozone layer, they tell us that it's starting to repair itself, that it's not quite as big as it used to be. How long is it going to take for it to completely go away? It could take a very, very long time, but we are making steps in the right direction. So this is where the hole in the ozone layer hangs out. Can you guys recognize that continent there? Okay, if you said Australia, well, you're close. It looks like Australia, but it's further south. This is Antarctica. Some of you probably recognize that right away. So we just are kind of lucky here that the hole in the ozone layer is hanging out in Antarctica. There are no humans that live year-round in Antarctica. There are animals there, plenty of penguins, and there are scientific outposts, meaning different countries, not the United States, I don't think. The Germans do have a scientific research station there. So there are scientists, that might spend some small portion of a year in Antarctica, but nobody lives there year-round. Nevertheless, we need to continue to work on letting this hole in the ozone layer repair itself. So I'm going to want you to know the average air pressure at sea level. And for this class, we're just going to learn it in PSI, which is pounds per square inch. You're not going to have to learn it in millibars or inches of mercury. So what is air pressure? I mean, how could we describe it or think about it? It's basically just the weight of the atmosphere above us. Okay, and the average air pressure at sea level is 14.7 pounds per square inch. Now, in reality, there are changes in air pressure from place to place all the time, and this produces wind. And what's going to happen to air pressure as you say climb higher and higher up on a mountaintop? Well, air pressure is going to decrease with altitude. Here's a graphic showing the curve of Our air pressure, or basically our atmospheric gases, is shown in red. And then, of course, Mount Everest is shown in the background, just to show you guys that, look at that dashed line, okay? So that is probably lower than base camp. Of course, there's more than one base camp on Everest, but the point being that when you get up there to one of those base camps and you're seriously considering trying to make it to the summit of Mount Everest, just know that you're already at an altitude that's so high that you've only got, you know, less than half of the atmospheric gases around you. So this is why the climbers are all going to have to carry oxygen with them. The only people that might not is that some of the Sherpas, you know, some of the natives living there, appear to be able to withstand the low oxygen, and some of them don't carry oxygen. All right, so structure of the atmosphere. There are 4 layers. You're going to need to know the first 2, okay? So you do need to know what's on this screen here. All right, so the troposphere is very important. It's the most important layer of the atmosphere to us because it's the bottom layer. This is where we live and breathe. And this is where all of the weather occurs. The weather is occurring in the troposphere only. And as you can imagine from, you know, looking at TV shows or movies where they're showing people climbing tall mountains like Mount Everest, and even in the summertime, there's snow up on the top of those mountains. That's because temperature decreases with an increase in altitude in the troposphere. So the environmental lapse rates, I'm going to ask you to know this, and I may end up making it an extra credit question. We'll see. Anyway, what does that refer to? It just means what is our average decrease in temperature with an increase in altitude? And that answer is average about 3.5 degrees Fahrenheit decrease in temperature for every 1,000 foot increase in altitude. Stratosphere, this is also on your exam, okay? It is the second layer up. It's above the troposphere, and it's very important to us. Why? Because this is where the ozone layer hangs out. You don't need to worry about what's in parentheses there. It's true that the temperature increases towards the top of the stratosphere, which is opposite of what it does in the troposphere. But I'm not going to ask you to know why that is for your last exam. And it has to do with interaction of sunlight and ozone. Why else is the stratosphere important? Because sometimes our large eruptions, as we discussed in class together, Mount St. Helens, Mount Pinatubo, occasionally even a shield volcano like that one near Lackey, Iceland back in 1783. Anyway, sometimes your large eruptions can spew volcanic ash all the way up into the stratosphere. And that means it's above the weather. And these particles are tiny, so it takes many months at least for those particles to settle back to Earth's surface. So that means they're stuck up there for a while, and they're blocking some of that incoming solar radiation, leading to a temporary temperature drop, as we discussed when we talked about volcanoes. So you don't need to know the mesosphere and thermosphere for your exam, but we will briefly discuss these. So the mesosphere is above the stratosphere, and the thermosphere is the last layer, the outer layer. It's above the mesosphere. And the outer limit is not well defined. What does that mean? It means that we don't really have a clear cutoff point where we go from Earth's atmosphere to outer space. Here is a graph of the thermal structure of the atmosphere. Okay, you don't need to worry about this other than what happens in the troposphere. So let's look down there at the bottom where you have Mount Everest. So temperature decreases with an increase in altitude in the troposphere. And also air pressure, again, remember, decreases with an increase in altitude in the troposphere. Okay, Earth motions. This is very important, and you need to pay special attention, and we may or may not have time for this in class during our alternate hybrid semester. Okay, so Earth has 2 principal motions, whole Earth motions that it does, and that are very important to life and modern society on this planet. First of all, Earth rotates on its axis. Everybody knows that, right? Now, how long does it take for Earth to do one complete spin? All right, everybody got an answer? 24 hours, right? And what does that give us? Our rotation on our axis gives us day and night. Earth also revolves around the sun. And of course, this is going to give us the seasons. And you guys know how many days? Don't say a year. Okay, yeah, we know that it takes the Earth a year to get around the sun, but how many days is that? If you said 364, well, you're close, but you're not completely accurate. It's 364 and a quarter days, which is why once every 4 years we have a leap year, and we have an extra day in February 29th. So the seasons are going to have nothing to do with whether Earth is closer to the sun or further away from the sun. As a matter of fact, Earth is actually closer to the sun during our winter in the northern hemisphere, and it's actually a little bit further away from the sun during our summer in the northern hemisphere. So the seasons are going to be the result of the changing sun angle throughout the year and the changing length of daylight. So take a look at this image here. In a normal semester, we would take time for this to talk about it in class, but this semester we won't. So on the left, notice the palm trees. They're trying to show us, say, within the tropics. So let's say that this is right at the equator. And this is going to be either the spring equinox or the fall equinox. And the sun's rays are going to be vertical, 90 degrees, straight up and down at the equator on that day. Now the image in the middle is going to represent more like 40 degrees north latitude. So we're talking Philadelphia, Pittsburgh. So this is some farm country, say in the middle of Pennsylvania, in between Pittsburgh and Philly. And on the first day of spring or fall, your sun's rays are only 45 degrees. So that's half of 90. So the intensity of the incoming solar radiation for the people there in Pennsylvania is half what it is for the folks at the equator at that time of year. And then, of course, the picture on the right is they're representing one of the poles, and which pole is it going to be? It's going to have to be the North Pole, because that's an igloo, and we don't have humans living year-round at the South Pole. So on the first day of spring or fall, the sun's rays are only 30 degrees, so they are 1/3 as strong as what you get at the equator at that same time of year. Okay, so I'd write down these first 3 bullets here, all right? So why do we have seasons? It's because the Earth is revolving around the sun, and therefore its orientation to the sun is changing, and we are going to have some diagrams to try and illustrate that. So in the short run, our angle of inclination is fixed. Right now we're going to average and say it's 23.5 degrees. It's really more like 23.45 degrees. And in the short run, the axis is always pointed in the same direction, meaning we point in the same direction all year long as we travel around the sun. Okay, so yet again, as we mentioned earlier, the seasons are not caused by the distance between Earth and the sun. Okay, you are going to need to know the dates for the solstices and equinoxes. And we're going to focus on the northern hemisphere because that's where we live. These are going to be short answer questions. Okay, I expect this to be review. You should have learned this at some point in your K through 12 education. We're going to begin with the summer solstice. First day of summer, longest day of the year. And these dates are good for Eastern Standard Time, I believe. And occasionally there's variations. And if you want to know exactly for upcoming years what date and what time of that day it's going to happen, you can go to the NOAA website. That's NOAA. And you can type in a search, and they have These calculated for probably, 10 years ahead in the future. Okay, so summer solstice in the northern hemisphere, June 20th or 21st. Where are the sun's rays vertical? You're going to need to know this as well. The sun's rays are vertical at the Tropic of Cancer, which is 23.5 degrees north latitude and runs through Havana, Cuba, just to give you, a landmark for a frame of reference. Now, let's go back to 40 degrees north latitude, say in between Philadelphia and Pittsburgh. On the first day of summer, this is as good as it's going to get for them for the sun angle. Okay, so the strongest angle of the sun's rays are going to be 90 degrees. But if you are not living within the tropics, if you don't live between 23.5 degrees north and 23.5 degrees south, then you will never see the sun's rays 90 degrees. So for people in Pennsylvania that really like summer and want to have strong sun rays, this is as good as it's going to get for them. It's only going to be 73.5 degrees. But when I lived in Morgantown, West Virginia, we would sometimes go see baseball games up in Pittsburgh. And I can tell you that Pittsburgh is a very hot place in the summer. All right, so how about the winter solstice in the northern hemisphere? Generally, this is going to fall on December 21st or 22nd. I think on rare occasions, sometimes it might be December 20th, like towards the very end of the day. This is the shortest day of the year for us in the northern hemisphere. The sun's rays this time are vertical at the Tropic of Capricorn, which is 23.5 degrees south latitude. Again, we will look at some drawings to make this more clear. Okay, so how about Pittsburgh on the first day of winter? The winter solstice, the shortest day of the year. The angle of the sun on that day is pretty low. It's only 26.5 degrees. And not only did I go to Pittsburgh occasionally to watch baseball games, I occasionally went to Pittsburgh just to hang out in the winter or to go to a hockey game. And I can tell you that Pittsburgh can be very cold in the winter. Okay, so how about our equinoxes? Okay, so the fall equinox is going to occur on September 22nd or 23rd. And where will the sun's rays be vertical? This time they'll be vertical at the equator, 0 degrees latitude. How about the spring equinox? The spring equinox will occur on either March 20th or 21st. Where are the sun's rays going to be vertical? Well, for the second day of the year, they will be vertical at the equator. Everybody knows that the equator receives the most of the sun's rays, and that it's the warmest part of the planet. Okay, so this is a really good drawing. So we're going to kind of talk our way through it, and if I move too quickly, then I recommend that you pause the video and go through it on your own, taking your time. Let's begin on the left. That is the summer solstice for the northern hemisphere, June 20th or 21st. And you see there that the northern hemisphere is tilted towards the sun, and the sun's rays are vertical. That arrow is pointing to the Tropic of Cancer, 23.5 degrees north. Now then, let's move down to the bottom, because that would be our next season. That's the fall equinox, September 22nd or 23rd. Of course, it never feels like fall in North Carolina on the first day of fall. No, that doesn't happen, especially not in recent years. Anyway, so on the fall equinox, the sun's rays are vertical at the equator. Okay, now the way they've drawn this, it's nighttime for us, but on the other side of the planet, the sun's rays would be vertical at the equator. Now let's go over to the right, because that would be our next season coming up as I record this in November. So now we're looking at the winter solstice, December 21st, 22nd. I want you to notice that the northern hemisphere this time is tilted away from the sun. Everybody see that? And where are the sun's rays vertical? Where do you have that arrow pointing? And the answer is pointing to the Tropic of Capricorn, which is 23.5 degrees south latitude. And then follow it up to the top, which is where you have your spring equinox. That would be your next season. And it's kind of hard to see, but the arrow is pointing again to the equator. And then, of course, you can travel over to the left again, and we would come back to where we started off at the next summer solstice. This is a nice image here because this is showing us the number of hours of daylight that you're going to get at various latitudes on your solstices and equinoxes. So let's start in the top left. Summer solstice. Okay, so look at 40 degrees north latitude, Pittsburgh and Philly, 15 hours of daylight. Those are some very long days. Notice that the equator has only got 12 hours of daylight. The equator is going to have 12 hours of daylight and 12 hours of dark all year long. But we're still on the top left image. I want you to look up there at 66.5 degrees. That's what we refer to as the Arctic Circle. Okay, how many hours of daylight does this say there? 24 hours. So if you've ever heard the phrase land of the midnight sun used to describe Alaska, that's why in the summer the sun doesn't set. Okay, now travel over to the far right. That's the opposite extreme. That is our winter solstice. Again, notice that the northern hemisphere this time is tilted away from the sun. On the summer solstice, northern hemisphere tilts towards the sun. On the winter solstice, northern hemisphere tilts away from the sun. So let's go to 40 degrees. Pittsburgh and Philly, only 9 hours of daylight. Okay, that's 6 hours less than they had on the summer solstice. Look at the equator, 12 hours again. Now go up to the Arctic Circle, 66.5 degrees. They have 0. So there's some amount of time a year during the winter that the sun just doesn't rise at all in the Arctic Circle. Now look at the bottom center image, and that one is showing both equinoxes, spring and fall. They're the same, so we can use one image here. Equinox, everybody is getting roughly the same hours of daylight. 12 hours of daylight, 12 hours of dark. Okay, heat transfer. Okay, yes, let's write these bullets down. This is important. We're not probably going to have time to talk about this in class, but it is important. Okay, so as we just described, Earth's surface is heated unequally. Everybody knows that. Okay, we get more heat at the equator and less at the poles. Well, the Earth tries to correct for this heat imbalance with the atmosphere and oceanic currents. Okay, so the atmosphere and the oceans actually transfer heat from the tropics towards the pole. They also transfer cold air from the poles towards the tropic. All right, so this imbalance in energy is going to drive atmospheric winds, global winds. It's also going to drive the ocean currents, such as the Gulf Stream, which is an ocean current that is off the east coast of the United States, and you may have heard of it. Okay, just very quickly, we'll go over atmospheric heating. I'm not going to ask you to know this for your exams. So at this point, we have a very brief physical science review, okay? So hopefully you've learned these things before in your high school career. Okay, so heat is always transferred from warmer objects to cooler objects. There are 3 basic mechanisms of heat transfer. The first one is conduction, which is molecule to molecule activity, as in transferring heat through touch. Okay, the second one there is convection. Sorry guys, I keep getting these texts about the election and I'm happy. Anyway, and I need not look at my phone because we got to finish this and then I can text my friends back. All right, so convection, mass movement within a substance. So this can take place in liquids or gases. So a good analogy here involving liquids is if you have a pot of water on the stove and you're turn on the heat and you're going to boil that water to make pasta or maybe, you know, some Kraft macaroni and cheese. But we also have convection within the atmosphere, in the gases. Okay, and then there's radiation. So we're talking about electromagnetic radiation here. So radiation is heat transfer, energy transfer, that you can feel but you can't see. All right, so you don't need to know this for your exam, but this is just a little snippet here on the electromagnetic spectrum, okay, going from the gamma rays, very short waves. Gamma rays, by the way, are very dangerous. I believe they're produced by supernova explosions, and yeah, they don't bode well for life on any planet. That's okay, they're incredibly rare that they make it all the way, say, to planet Earth. Then you got X-rays, of course. Any number of us have had X-rays at times. If you had a sports injury or fell out of a tree, or like me, if you accidentally totaled a car, and they're going to do X-rays and make sure you don't have any broken bones. And then there's the ultraviolet radiation coming from the sun. And part of that ultraviolet radiation is visible, what we call white light, as in that's what makes things bright in the daytime. And then you've got infrared radiation, near and far infrared radiation, which is basically heat, energy that you can feel but not see. And then, of course, there are microwaves and radio waves, which both are very useful. So this one image here is a great way to kind of sum up heat transfer. So you're camping with friends in the mountains in November, and you are going to make pasta. So you're boiling that water. Okay, so the convection is, of course, the boiling water and the black arrows there. The conduction is the fact that if you don't use a pot holder, and this is, you know, all metal, you're going to feel the heat from that pan touching your hands pretty quickly. And then the radiation is that heat coming from the fire that you can feel but you can't see. And then if you want to, you can pause here and take a look at the electromagnetic spectrum. I have to admit that physical science and physics, I think it's very fun. And if I had chosen a science other than geology, I think it would have been physics. Okay, atmospheric heating. You should write down bullets 2 and 3. Yeah. Okay, so now we're going to have a discussion on how the troposphere, or how the air around us, is heated. Okay, so it begins with short wavelength radiation coming from the sun in the form of ultraviolet rays. So it turns out that the Earth, land and sea surfaces, are going to absorb 50% of that incoming solar radiation, the short wavelength ultraviolet radiation. And then that 50% that we absorb and make use of, the Earth is then going to spit it back out at a longer wavelength, and then the greenhouse gases are going to trap it. So this means that we lose 50% of the incoming solar radiation, and that's okay. We have plenty enough solar radiation. We don't need any more. So what happens to the other 50%? It's either reflected back to space, scattered into tiny particles, or absorbed by atmospheric gases. Now, white light, as in visible radiation, most of that reaches Earth's surface. So here's a nice little graphic just showing how we manage to lose 50% of that incoming solar radiation. If you want to, you can pause and take a look at this, but I'm going to move on. Okay, so this is important. I would write down both bullets here. So how the troposphere is heated. Here's what's important. The atmosphere around us, the air around us in the troposphere, is not heated directly by that short wavelength incoming solar radiation. You know, is that radiation coming to the surface of our planet? The answer is yes. And we see it in the form of white light, but it's not directly heating the air around us. Okay, so this is a two-step process. So the first step is that land and sea surfaces will absorb this 50% of the incoming short wavelength solar radiation that we receive from the sun. And then what happens, and there is some lag time to this, which is why the high temperature of the day doesn't occur, at noon when the sun is high in the sky, but it's going to occur in the afternoon, more like, 3 to 4 p.m. So the Earth will kind of re-radiate or spit back out this radiation, but it has changed to a longer wavelength because the Earth is not as hot as the sun. All right, and this is important that it gets changed to a longer wavelength. By the way, we refer to this as terrestrial re-radiation, meaning that the Earth is re-radiating this energy back out to the air around us at a longer wavelength. Okay, I would write down the first two bullets here. So then the second step in this process is that the greenhouse gases in our atmosphere will then absorb and trap this long wavelength radiation. And also to some extent, just kind of reflecting it back to us on the surface. So this terrestrial re-radiation gets trapped in the troposphere and heats the air around us. It's referred to as the greenhouse effect, and this is not actually how a real greenhouse works. We don't have time for that, but that'd be an easy Google search to find out how an actual greenhouse works. But that's what we call it. We call it the greenhouse effect, and it is the greenhouse gases that trap in this heat. Which might beg a question, and then does that heat get trapped in the troposphere forever? And well, no, of course not, right? Everybody knows that overnight it gets colder. So roughly when do we experience our overnight low temperature? And the answer is shortly before sunrise. That's when you're going to hit the low temperature. So this is a nice graphic, and I like the fact that they've used a color change. So on the left in the yellow, that's your incoming short wavelength, high energy ultraviolet radiation from the sun. That's the 50% that we do get to keep. And then over on the right, in the red arrows that are now not just shooting back to space and just kind of hanging out, that is our terrestrial re-radiation. Okay, so that is that radiation from the sun, then spit back out from the Earth at a longer wavelength and then hanging around because it's being trapped by the greenhouse gases. Okay, these are the 5 greenhouse gases. I believe on the exam, I'm going to ask you to be able to give me 3 of them. This is going to be a short answer question, okay? The first 3 especially, everybody should know these kind of off the top of your head when we are finished with this semester because it's very important. And we don't want to have too many greenhouse gases on this planet because, well, quite frankly, that drives climate change and global warming. Okay, so water vapor. Remember we said that water vapor was our most important variable component of the atmosphere? This is one of the reasons why. It's a greenhouse gas. And then there's carbon dioxide, which is a greenhouse gas. And again, our current percentage is more like 0.04%. It's risen a lot in the 12.5 years that I have taught here at UNCP. Then there's methane, natural gas, CH4. Wow. So the levels of methane are lower percentage than carbon dioxide, but here's what's scary about methane levels and the fact that they're increasing is that methane is the most powerful of the greenhouse gases. And it is as much as, gosh, let me see if I can get these numbers correct. And they do change from time to time, and certainly, of course, you could do a Google search. I believe it's something like methane is anywhere from 6 to 24 times more powerful a greenhouse gas than carbon dioxide. Then there's nitrous oxide and hydrofluorocarbons, which we use for propellants instead of the CFCs. Remember the CFCs put a hole in the ozone layer? So we quit using those, but what we're using instead doesn't put a hole in the ozone layer, but it's yet another greenhouse gas. Sometimes when you fix one problem, you add to another. You can stop on this slide if you would like. I would prefer an image that went back further, and actually what I might tell you to do is to do a Google search for, say, Google Images, and type in Vostok ice core data. And the Vostok ice core gives us information on, that's from Antarctica, by the way, gives us information on carbon dioxide levels and air temperature on this planet going back 800,000 years. And we see that we have ups and downs that are expected due to Milankovitch cycles. And then you get to the Industrial Revolution, which, you know, historians will tell us starts anywhere from, I guess, mid to late 1700s, really. And then you get to recent decades, and the temperatures and carbon dioxide levels shoot way above anything that we saw in the background in the last 800,000 years. So here are some, and even this is kind of old. Notice this goes back 2001. That's okay, it's still valid. It's just that more could be added. And what's kind of cool about showing this older information here is that in 2020, yes, we've seen a lot of these things happen. But I recommend pausing the video and taking a look at this. Oh, I keep getting more text messages. It's a beautiful thing. They probably wonder why I'm not texting them back. Okay, so controls of temperature. Even in a normal semester, this is something that I usually make into extra credit because I don't have time to cover it. So in our pandemic years, yes, I'm thinking of it as years, not semesters, just being realistic. Anyway, we will make this extra credit. Okay, so what I would write down, or I guess the last 4 bullets here for extra credit. All right, so controls of temperature. Of course, the most important one is the amount of solar radiation that you get. You know, in other words, where do you live? What latitude do you live at? But another one, and a fun one, is called the differential heating of land and water. And if you take the weather and climate class, either with me or Dr. Edgel, later on, then we'll discuss this in more detail. It's a lot of fun, okay? So here's how it goes. Water will heat up more slowly than land, but will also cool more slowly than land. And of course, the opposite is true. Land will heat more quickly than water, and land will cool more quickly than water. So there's greater variation in temperature, say throughout the year or throughout the day, over our continents than over our oceans. All right, so this is a neat little graphic here. So we are comparing Vancouver, Canada to Winnipeg, Canada. Notice that they should be at pretty much the same latitude. Okay, but they're different locations. Vancouver is on the coast. It's on the west coast, so it's on a windward coast. And then Winnipeg is in the middle of the continent. Okay, so I want you to look at their temperature curves throughout the year, and they go from January to December. So in the middle is your summer months. Winter is on the either end. Okay, so let me ask you some questions. Okay, who has the coldest winters? Okay, the answer is Winnipeg in the blue. All right. Vancouver has milder winters. Okay, now for the next question. Who has a hotter summer? Everybody see that in the middle? Yeah, Winnipeg. Okay, so just in general, Vancouver, their curve is more flat. Why? Because they're on the coast, so they have the moderating influence of a maritime environment. Sorry, I meant to say, then there's albedo or reflectivity. Sometimes I forget to not go to the next slide until I stop talking. You may pause here and look at this if you would like. It's actually kind of fun. You see that your more light colored objects like a fresh fallen snow or white sand are going to reflect more, and then darker colored objects like water, dark soil, road, blacktop, those are going to reflect less, means they will absorb more solar radiation. And then here is something I was describing earlier. The presence of clouds can reduce the daily temperature range. So in the top one there, the high of the day will not be quite so high because you got clouds. That's a beautiful thing in the summer. And then in the bottom there, your overnight low will not be so cold if you have clouds. And that's a beautiful thing in the colder months. Remember, a clear night is always colder. You see the stars, but you put on a coat. Okay, how about let's take a look at altitude. Okay, so here we're going to compare Guayaquil. These are both in Ecuador, I believe. Okay, Guayaquil is at sea level. Average elevation is 150 feet. And then Quito, also in Ecuador, is up in the mountains, the Andes Mountains, and it's more at 10,000 feet, which is pushing 2 miles elevation. So look at their temperature curves. Which one is colder all year long? Quito, because it's up in the Andes Mountains. Which one is warmer? Guayaquil. Notice that both curves are pretty flat. Why is that? It may not be so obvious in this image, so it's kind of an unfair question, but some of you are going to get it right anyway. They are close to the equator. Here's another example of geographic position. Okay, mountains acting as a barrier to the moderating influence of a maritime environment. So you got Seattle, Washington, and Spokane, Washington. They're both about the same latitude. Seattle is on a coast, and it's on a windward coast, so we expect less temperature variation throughout the year on the west coast than the east coast. And then Spokane, Washington is further east, and there's a mountain range in between. It's called the Cascades. So the Cascades basically cut off Spokane from that moderating influence of a maritime environment. So Spokane has colder winters and warmer summers than Seattle. Seattle, everybody knows, is known for a lot of clouds and rain. I could live there. Here's another example of geographic position. So on the west coast there, that's a windward coast, meaning that the United States are in a band of winds known as the westerlies. Winds are named for the direction from which they're coming from. So our winds blow from west to east. So we're in the westerlies. That means that the west coast gets more of this moderating influence of a maritime environment than New York City does, because New York City is on the east coast. It's still a coast. Okay, so if they were to add a third city, like St. Louis, Missouri, more in the middle of the continent, we would see that St. Louis would have probably colder winters and hotter summers for sure than either coast. But here, the way it's drawn, we're just going to compare these two coasts, and notice that New York City has hotter summers and colder winters because they're on a leeward coast, meaning the winds are blowing from the land to the ocean offshore. Eureka, California, you kind of got to like the temperature you have, because it's not going to change a lot. Although I think those temperatures look pretty good. Okay, so Milankovitch cycles, this is a lot of fun. And even in a normal semester, we rarely have time to look at it. It's definitely not on your exam, but I'm going to briefly talk about it, because this PowerPoint will also be used for all my future online classes in the summers. Okay, so Milankovitch cycles. There's 3 different types of Milankovitch cycles. These things, by the way, are the background control over whether we are in an ice age or not. So first is precession, saying that basically when we say that Earth, the axis points in the same direction over the course of a year as we go around the sun, we say that the direction we point in is fixed. Just know this, that's in the short run. In the long run, it varies. So the poles wobble over time. It has to do with the pull of the sun and moon acting on the equatorial bulge. The cycle's on the order of 25,800 years. So currently, our North Star is Polaris, but 12,900 years ago, the North Pole will have swung around 180 degrees. And at that time in the future, our North Star is going to be Vega. Oh, my mom is calling me. Are you kidding me? This was a bad day to start this PowerPoint, but I didn't know we were going to get news already. Anyway. Okay, so I will have to call all these people back after we're done. This could take us another hour. All right, so just an interesting thing here on that third bullet. Again, none of this is on your exam. Okay, so currently, perihelion, the time when Earth is closest to the sun, is on January 3rd during our winter in the Northern Hemisphere. And it also means that aphelion, the time that Earth is furthest from the sun, is during our summer. And this is really good for us in the Northern Hemisphere because this means that our winters and summers are a little bit more mild than they would be if it was switched. Well, guess what? It's going to be switched 12,900 years from now. And my cat is on my lap and she's putting her paw on the mouse pad. We cannot let that happen because then it will erase this recording. Okay, anyway, 12,900 years from now, this will be opposite. And then the people in the southern hemisphere will have milder summers and winters than we do. Is there that much difference in how mild it is? No, not really. Here's our second Milankovitch cycle, the shape of the orbit, also known as eccentricity of orbit. So our orbit is elliptical. Again, it's not a perfect circle, but sometimes it's more elliptical, sometimes it's less, and it has to do with the pole of both Venus and Jupiter, but Jupiter more so because it's a really big planet. Everybody knows that, right? Okay, so these cycles are really, they're kind of confusing to figure out. We talked about these once in a grad class that I took. It was a isotope geochemistry class. It's kind of hard to figure all this out. But so you got cycles on the order of 95,000 years, but with larger superimposed peaks at 125,000 and 400,000 years. When the orbit is more elliptical, meaning less circular, perihelion is closer to the sun and aphelion is further away than when the orbit is more circular. So basically this is saying that when the orbit is more elliptical, your difference between winter and summer in the two hemispheres will be greater. And then the third and last Milankovitch cycle has to do with Earth's tilt, okay? So they refer to this as axial tilt or obliquity, and currently it's 23.44 degrees. We just kind of round that to 23.5. But even that is not fixed in the long run, so it can vary. We kind of wobble a bit. It can vary between as low as 21.4 degrees, but as steep as 24.5. And this cycle varies over the course of 41,000 years, and this also has to do with pull of gravity of planets around us. And it affects the difference in severity between winter and summer in each hemisphere. So these Milankovitch cycles, guys, are these are the background controls. These are the short-run background controls over whether or not Earth is in an ice age or a warming period. There's another longer-run control which has to do with placement of the continents. Remember, the continents move super slow. Yeah, Milankovitch cycles. They're actually a lot of fun, and I recommend pausing here and taking a look at these drawings. This one slide here shows the differences pretty well. It's interesting stuff. Okay, so we are now going to talk a little bit about clouds and precipitation. Okay, again, this is no longer chapter 12. It's whatever chapter, it doesn't matter. You guys are smart, you will figure it out. Okay, so you don't have to write any of this down. This is kind of a repeat of something that we did at the beginning. Water vapor is a variable component in our atmosphere, and it's the most important gas in the atmosphere. Well, the most important variable gas, because it's a greenhouse gas, critical to heating in the atmosphere, but it's also our source of condensation and precipitation. Here we're going into another quick review of physical science, and this won't be on your exam. Well, an upcoming slide might be. I'll let you know when we get there. This should be a review. All you guys know this. 3 states of matter, solid, liquid, gas, but we will focus on not just any matter, but water. And to change from one state to another, you either are going to have to add heat, as in it's being absorbed, or you're going to have to release it. Okay, evaporation and condensation. I would write these down, but just the first bullet that goes with each. In other words, I'm not going to ask you to know if heat is added or taken away. And I'm certainly not going to ask you to know how many calories per gram of water are added or taken away. Just know this, which you already know. So this is a review. Evaporation, liquid changing to a gas. This does cause a cooling effect, and this is why our bodies sweat, to bring down our core body temperature, because it's not so much the sweating part, but the atmosphere absorbing the sweat off our skin, which is absorbing heat energy off of our skin and cooling us. Condensation of course, is very important in our atmosphere. Water vapor, which is a gas, changing to a liquid. This is going to be the source of clouds, fog, and eventually precipitation. Melting and freezing. You already know this, so I'm not going to be on your exam. We know melting is solid changing to a liquid, and freezing is liquid changing to a solid. Okay, sublimation and deposition will be on your exam because these are potentially new topics for you. So you want the first red bullet there for each of these. Okay, so sublimation is a solid changing directly to a gas with no liquid in between. A good example here are ice cubes that shrink in a freezer. If you use a lot of ice, you have no idea what I'm talking about, but my teeth are sensitive, so I go ahead and make ice. Really, it's just so that I can have ice in the freezer when the hurricane comes and I lose power. It's rare that I get ice out to put it in some kind of a drink, maybe an iced chai latte. And then I'll notice that the ice cubes are small because it was, you know, weeks or months ago when I filled up the tray. Another example is dry ice, frozen CO2 sublimating to a vapor. Deposition might also be new for you. This is water vapor, a gas form changing directly to a solid. And an example is frost in a freezer compartment. But these days, most freezers, refrigerators with freezers, everything in this country and probably most other countries is frost-free. But my grandparents had to defrost freezers from time to time, and I remember watching them do that when I was a little kid. We can skip this slide here. Okay, humidity. Yeah, we need the first three bullets here. Even though we're going to focus on relative humidity, we still need the first three bullets here. Okay, so humidity refers to the amount of water vapor in the air. That's what we call it if it's just simply humidity. Although we will be learning relative humidity very shortly here. So saturated air means that that air is filled up with water vapor to its capacity, meaning it's holding as much water vapor as it can hold at that temperature. That's what we mean by it's at capacity. We refer to that air as saturated. And then that third bullet there is something that we all know from living in the South. Capacity is temperature dependent. Warm air can hold a lot more water vapor than cold air. You can skip the last bullet there. You can skip this slide, or you can pause here and look at it if you want to. This is just proving to us, looking at temperature of the air mass there in Fahrenheit, you're going to go from -40 to 104 degrees, and just showing how many grams of water vapor per kilogram of air that air mass can hold. So indeed, as that air temperature rises in our warmer months, it can hold a lot more water vapor, and that means that you can have really high relative humidities and the air can feel nasty. Okay, so relative humidity. Yeah, you need that bullets 2, 3. Well, really you need all of this. Okay, how about you can skip the first bullet? That might be easier. So relative humidity is how we typically express humidity. And this is how all of your news organizations that have a weather report or the Weather Channel or the National Weather Service, I mean, they're all pretty much, I mean, some of those might also give you absolute humidity, but they're all going to report relative humidity. It's a good way to describe the moisture content of the air, and we kind of know what that feels like. Okay, so it's a ratio of the air's actual water vapor content compared to how much water vapor it could hold at that temperature. Okay, so it's expressed as a percent. All right, and if the air is saturated, then that means you've got 100% relative humidity. So on a day that you've got 100% relative humidity, the air is thoroughly saturated, meaning it's holding as much water vapor as it can at that temperature. Okay, that also means that probably it feels kind of nasty, especially if it's a warmer time of year, and it also could mean that you've got rain or maybe dew out there on the blades of grass if it's in the morning. So relative humidity, definitely going to want you to know that for the first exam. For your last exam, and if you're not finished writing this down, just pause the video. Okay, you don't have to write this down and you don't need to know this for your exam, but just a quick discussion here. There are two ways that you can change relative humidity. Okay, you can either add moisture or take it away. If you add moisture, it raises the relative humidity and you get closer to saturation. If you take away moisture, it's going to lower the relative humidity. And the other way you can change relative humidity is with a change in air temperature. Okay, so this is converse of what you might think. If you lower the air temperature, it will actually raise the relative humidity. And if you raise the air temperature, it will lower the relative humidity. And again, this is because warm air can hold more water vapor than cool air. We are skipping this slide for sure. Dew point temperature. Yeah, we need everything here. So, you know, if you don't get it all written down while I'm still, and I go to the next slide, just pause the video. Okay, so dew point temperature is important. All right, so what does it mean? Well, first of all, it just means the temperature to which a parcel of air or the air around you or above you would need to be cooled to reach saturation, to reach 100% relative humidity, okay? So why is dew point temperature important and why do we bother to monitor it every day and several times a day? Because if you cool the air to or below the dew point temperature, then you're going to hit 100% relative humidity, you're going to hit saturation, and condensation will begin, okay? So this can be dew on the blades of grass in the morning, this could be fog, which if you're driving through fog, you want your headlights on, but they need to be on low beam, not high beam. And of course, also cloud formation comes from condensation. You don't have to write down what's in bullets there, but it's just a reminder, when you see clouds in the sky, well, that's not just water vapor, okay? That's some solid form of H2O. It's either going to be water droplets or ice crystals, or it could be a mixture of both. Now, an important thing here is that water vapor requires a surface to condense upon, and that's why our condensation nuclei, aerosols in the atmosphere, that's kind of how they help us out. Here's a nice graphic, not on your exam, but you can pause and take a look at it. And this is just showing you that as the air temperature drops, let's see, let me get this right. As the air temperature drops, the relative humidity increases, and as the air temperature rises, the relative humidity decreases. So you're looking here from midnight to midnight, okay? So noon is in the middle. So this is a 24-hour period from midnight, say Tuesday night, to midnight Wednesday night. And you're looking there as your temperature varies throughout the day, as we expect it to, that your relative humidity will vary as well, but it will be conversely, kind of like a mirror image. Okay, adiabatic heating and cooling. Okay, I believe I'm not going to test you on what these terms mean. So first of all, what does adiabatic mean? So adiabatic temperature changes mean that you're changing the temperature of an air mass either by compression or by expansion. In other words, you're not adding heat or taking away heat. That's what adiabatic means. And we don't need to get into that much detail on our exam. So what we'll focus on is just, air masses heating and cooling. And this is happening because they are either rising or they are sinking. That's how we're going to think about it, okay? So cool air is more dense than warm air. Cool air will descend or sink. But as a cool air mass is sinking towards the surface, it's being compressed, as in you're adding molecules, air molecules, to the mix. So you're compressing them, you're squeezing them together, and that's going to warm that air mass. Okay, and then the opposite is true. When you have a warm air mass at the surface, it's going to rise because it's less dense than the cooler air around it, just like a hot air balloon will rise, okay? So you have a warm air mass at the surface. As it rises, it's going to expand, as in less air molecules, and it will cool due to that expansion. Bottom line here, cool air will sink and will be warmed along the way, and warm air will rise and will cool along the way. All right, a quick snippet on clouds and cloud formation. Let's write down bullets 2 and 3, okay? You can skip the first bullet, because you know what clouds are. If you need to write it down, you can, but I think we wrote this down on a previous slide. Yeah, this is going to be a 2-hour PowerPoint. I knew it. That's okay, it's important. All right, so clouds, again, when you're looking at clouds and not just blue sky, well, then it's either going to be water droplets, ice crystals, or both. You know, at that point, what you're looking at is not water vapor anymore. Now, so even when you have enough cooling that your air mass reaches the dew point temperature or falls below, you're not just immediately going to have condensation unless you have some kind of nuclei, okay? Condensation nuclei, because I'm trying not to laugh at something that a friend of mine just texted me. Okay, at things going on in our country. Oh, it's funny. I wish I could share it, but I shouldn't. Okay, so water vapor needs a surface to condense upon. Okay, so this could be your glass of iced tea. It could be the windshield of your car or the blades of grass outside if it's dew in the morning, or it could be condensation nuclei, aerosols like dust or pollen in the atmosphere. So what is the most important control of cloud formation? Adiabatic cooling, which just means that the air is rising, it's lifting, and it's cooling, okay? Again, you don't have to worry about the term adiabatic. It just means it's cooling because it's expanding. The rising air mass will cool, and you will reach the dew point temperature, and condensation will occur because you do have condensation nuclei present most of the time. All right, so here's a nice little graphic. You've got a hot pocket of air at the surface, 32 degrees Celsius. It's warmer than the air around it. And as it's rising, notice that gray bubble getting bigger. That is just showing that the air is expanding. And look at the temperature. It's cooling. And then there, where the red and blue arrows meet, that's your lifting condensation level. You have now reached the dew point temperature. Condensation will begin. And you can grow a taller cloud like a cumulus congestus or eventually a cumulonimbus cloud. If that air mass continues to still be warmer than the air around it, it'll keep on rising, it'll keep on cooling, and you'll get more and more condensation, and you can build a tall cloud. All right, so let's write down the middle bullet here. All right, I think we got that first bullet pretty well. When air rises, it's going to expand and it's going to cool, okay? We are next going to be discussing the lifting mechanisms. There's 4 basic lifting mechanisms for air to rise, all right? That middle bullet is kind of important. So clouds will develop when that air is rising and cooling, and it cools enough that it will reach or fall below the dew point temperature, and then it is 100% humidity and saturated air, and then condensation will occur. Okay, so 4 processes that lift air. We're going to begin with the first 2. We need every bullet here. So again, if I talk faster than you can write it down, there's no worries in the online room. You just pause that video. I do that in the grad class that I take at NC State. I have to pause on every slide and write everything down. So if you're doing the same, don't feel bad. You're in good company. Okay, so the first one is the most fun. It's called orographic lifting, and it has to do with mountains. Okay, so elevated terrains, mountains, yes, they can act as barriers, but what's important here is that having a mountain range present is a lifting mechanism. And we're going to have a drawing coming up on the next slide, and you're going to see that if you have air moving towards your mountains, it can't go through the mountains, so it's going to go up and over the mountains, and it's going to cool on the way, and you're going to have condensation form clouds and have rain. A good example is Seattle, Washington on the west coast, and then you got the Cascade Mountain Range there just to the east. Okay, next is frontal wedging, which happens all over the place. It happens in our area all the time. And it basically is going to have to do with a clash of warm fronts and cold fronts. And I'll describe this one more when we are looking at a drawing of it, which will be coming up soon. Okay, and frontal wedging is involving fronts, warm fronts and cold fronts. And these are part of our big storm systems we refer to as mid-latitude cyclones, which we will be discussing before this PowerPoint is done. Okay, so we're not to our drawings yet. I guess they're coming up on the next slide. Okay, so our third process that lifts air is something called convergence. Yeah, we need every bullet here. Okay, so convergence is exactly what it sounds like. Kind of like, remember continent to continent convergence? Well, in this case, you've got convergence of air. So when you have air from at least a couple different directions moving towards each other, flowing together, well, you get this, basically this bottleneck of air molecules, and there's no place for it to go but upwards. So this is a lifting mechanism, all right? And the best example is Florida, because Florida is a big peninsula, and you have air moving from the Atlantic over the land, and air moving from the Gulf over the land, and the air is going to converge over Florida, and then it's going to rise, and you're going to end up with many days of thunderstorms. I think on average they have about 100 days per year of thunderstorms in Central Florida. That's roughly one thunderstorm every 4 days. That's a lot of thunderstorms. And our last type of lifting is called localized convective lifting. So this basically has to do with hot pockets of air at the surface, which they might refer to as thermals. And how do you end up with air warmer in one place than around it? And it probably has to do with what kind of surface features you have there. You know, like, is it a big, huge parking lot like you might find at Carowinds, you know, versus a snow-covered field? Now for our drawings. Oh, they're all together. That's kind of cool. Okay, so let's begin on the top left. That's orographic lifting. Let's say that's Seattle, Washington. You have, and again, we are in a band of winds known as the westerlies. So you have warm, moist air coming off the Pacific Ocean, moving east. It comes across Seattle, and then it immediately hits mountain ranges. And that air is forced up and over the mountain range. And as it's forced up, it's cooling. You have condensation, you form clouds, and you get plenty of rain in Seattle. And then that air mass continues to flow to the east. And when it gets to the other side of the mountains, it's lost most of its moisture. It's now dry. And this is what we refer to as a rain shadow desert. Okay, now we're going to B, which is on the top right. So what you have here is, let's say that Pembroke is right there where it says cold air. So you got a cooler air mass over top of this at Pembroke on this day. But there's a warm front moving in from the west. So a warmer air mass is moving in. And right there where they touch is the front. So what happens here is that the warm air mass is less dense than the cold air. So that wedge of cold air kind of acts like an invisible mountain range. And the warm air coming in behind it from the west is pushed up and over the cold air. And as it rises, it's going to cool, you're going to have condensation, and you could produce rain. Okay, bottom left, C, this is convergence. There's Florida, your big peninsula, and you've got air moving in, moist air from the Atlantic and from the Gulf, and they're converging, and there's a bottleneck, and it's pushed up, and you get plenty of condensation, rain, and thunderstorms. And then on the bottom right is localized convective lifting, and you got a couple of hot pockets of air here that are rising. And that one on the left has risen far enough to reach the condensation lifting level and form clouds. Okay, stability. Even in a normal semester, we don't have a lot of time to really cover stability and instability, but we are briefly going to discuss them since the PowerPoints are here. But I'm not going to ask you about stable versus unstable air. And this weekend, one of my jobs, other than narrating the last 2 PowerPoints for my classes and doing my last homework for my grad class, I also have to figure out exactly what it is we're going to cover in class together this week for this PowerPoint. We're only going to be able to do a portion of it. Okay, so you don't need to write any of these things down, but stable air is basically just air that you know, isn't rising. Okay, it's resisting vertical displacement. Why? Because it's cooler than surrounding air. It's more dense and it wants to sink. So if it's not rising, then it's a stable air mass, meaning that you have really zero chance of any afternoon thunderstorms. Okay, so what might you get? Well, you might have fair weather, blue skies with a handful of cumulus clouds. Those are those puffy white clouds that look like cotton balls in the sky. Sometimes you might get some widespread thin clouds, and you're generally not expecting to get precipitation. If you do, it's going to be very light. Unstable air. So again, this is not on your exam. There's actually already a video lesson up for the mid-latitude cyclones and the warm front and the cold front. Maybe some of you watched it already. I don't know. If not, you gotta watch them this week, getting ready for your last exam. Okay, so unstable air, not on your exam, although I may refer to unstable air later with our warm fronts and cold fronts. Air that is rising, okay, for whatever reason. It could just simply be that it's a hot pocket of air, warmer than the surrounding air, and therefore less dense. Or it could be that you have one of those other lifting mechanisms like orographic lifting. So rising air is considered potentially unstable. Why? Because it's going to keep on rising until it reaches an altitude where it's at an equal temperature. So that means that, of course, as it rises, it's going to cool, and you are expected to get condensation and cloud formation. And if that air is really unstable, then you can build cumulonimbus clouds and an afternoon thunderstorm. Okay, so clouds, there's nothing about clouds that I'm going to put on your exam save for a couple of them. Okay, so the cumulonimbus clouds and the nimbostratus clouds, and maybe the cumulus clouds. So 3 clouds. I'll let you know when we get to those slides. Right now, you don't have to write any of this down. What are clouds? Well, they're millions and millions of tiny water droplets or tiny crystals of ice, or both. There are many different cloud types, and they're based on 3 forms, okay? But also based on altitude, which we'll talk about on the next slide. So cirrus clouds are high, thin, wispy ice crystals, kind of look like feathers up in the sky. Cumulus clouds, these are the ones that look kind of like cotton balls in the sky, or cauliflower. Globular cloud, flat base, and have a rising dome or tower. And then stratus clouds. Stratus, like strata, like layers of rock. Okay, so sheets or layers that cover much of the sky. Let's go back and redo this. Cirrus clouds approaching from the west are signs that you have a low pressure system moving in, which is going to be in the form of a mid-latitude cyclone. Here are your cumulus clouds, also known as fair weather clouds. Okay, stable air, good day for a picnic or a day at the beach or an outdoor concert. They look kind of like cotton balls in the sky. Altostratus clouds. So your clouds are not only based on the form, cumulus, cirrus, or stratus, but also based on the altitude. High clouds, middle clouds, low clouds. Also not on your exam. Cirrocumulus clouds, altocumulus clouds, nimbostratus. Nimbostratus is one of the clouds that is going to be on your exam. Okay, so take a look at this. Is it going to rain? Yes, it is. Okay, so nimbostratus clouds are associated with rain, and they are associated with our warm fronts. Okay, that's what I'm going to want you to know about nimbostratus clouds for your exam. And I'm going to bring up the cumulus clouds from a few slides back. I forgot to mention that they are potential exam material. The cumulus clouds, the puffy white cotton ball clouds, are associated with fair weather. Now your cumulonimbus clouds, this is your 3rd type of cloud for your exam. Okay, everybody knows what these look like, right? Those are really tall clouds, and you know they mean you got a thunderstorm brewing. When I was growing up, we called them thunderheads. So cumulonimbus clouds are associated with thunderstorms, and those can either be your afternoon thunderstorms or your intense thunderstorms that come along with the cold front. But basically, bottom line, I want you to know that cumulonimbus clouds are associated with thunderstorms. If you want to pause on the slide, you can. Basically, it just showed you the nimbostratus cloud, which is not exactly the same as the stratus cloud. The stratus cloud is when your sky's, pretty much covered with clouds, but you're not expecting rain. The nimbostratus clouds are rain clouds. They're not thunderstorm clouds, but they are rain clouds. And here's a nice image showing all the different types of clouds together. Okay, fog. How about let's write on the middle bullet here. That's all I'm going to ask you to know about fog. I mean, we know what fog is, right? It's a cloud that's at the surface or very close to the surface. They tend to form maybe in the evening, sometimes overnight or early in the morning, due to something called radiation cooling, which just means that the surface of the Earth is cooling off overnight. And of course, fog is a hazard, right? When you're driving in fog, you should have your headlights on, not off, but they need to be on low beam, not high beam. So you're not going to need to know the types of fog, and we don't really have time for it ever for the earth science class in any semester, even when it's not a pandemic. If you take the weather and climate class, we'll talk more about the types of fog. They are kind of fun. You don't have to write them down. We'll discuss them briefly. Advection fog. Warm, moist air moving over a cool surface, like warm air from the Pacific moving over the cold California current there in San Francisco Bay. Radiation fog or surface cooling rapidly, particularly overnight on clear nights, giving you fog in the early morning. And then upslope fog is basically like orographic lifting, humid air moving up a slope, meaning moving up over the mountains. So do we expect to get fog in the mountains more often than we might get it, say, in the coastal plain? And the answer is yes. I grew up in the mountains. I know this to be true. Here's a nice image of advection fog over San Francisco. Here's an image of radiation fog cooling overnight. Here's an image of upslope fog in the mountains, not the Appalachians. Okay, we will skip this one here. We definitely don't have time to cover types of evaporation fog. You are welcome to pause and read over this if you would like to. If you end up taking the weather and climate class, we will briefly discuss the steam fog and frontal fog or precipitation fog slightly. Steam fog. So I will just go ahead and mention that when I lived in Laurinburg, very depressing place to live, no offense. Anyway, on my drive to school in the morning sometime, there's many lakes out there on 74, and I would see steam fog relatively often. Okay, precipitation. The only precipitation you're going to need to know for your last exam is going to be hail. Okay, so we are very quickly going to go through the types of precipitation. All right. And of course, cloud droplets, rain, everybody knows what rain is. There are different sizes of rain. This is not on your exam. The smallest is referred to as mist. Cloud droplets have to go through about 1 million collisions to become big enough to actually fall to the ground, believe it or not. And of course, snow. We don't get snow here often. I always want to get snow in the winter here, and it's so rare. Of course, I guess when we do get it, the best thing to do is to cancel everything because nobody knows how to drive in that snow, and we don't have the resources in the South to take care of that snow. Anyway, snow, ice crystals in your clouds, and they are not melting on the way down. By the way, interesting thing here is in the middle latitudes, like where we live, most of our precipitation actually begins as ice crystals in the cloud and melts on the way down, and then hits the top of our head as a rain droplet. So we will not take time to discuss collision coalescence versus the Bergeron process. Not on your exam, but just know that collision coalescence is something that happens in the warmer latitudes, like within the tropics, or might happen after your ice crystals have fallen from the cloud and melted on the way down. and just that the droplets can grow larger as they collide with others and get bigger. Okay, so rain has, well, basically a typical diameter, like 0.2 inches across. We're usually expected to get rain when we have nimbostratus clouds in place, like along a warm front, or when we have cumulonimbus clouds, we're about to have a thunderstorm. Drizzle are just tiny rain droplets. Again, mist is the smallest of drizzle. Of course, snow. Hope we'll see snow this winter. I don't think we will, though, because it is La Nina. Okay, sleet and freezing rain or glaze. We should write this down. Oh, I just remembered. Yes, hail is definitely going to be on your exam. I can't remember if sleet or freezing rain are on your exam, but I do want us to discuss them, and I'd like you to write it down. Okay, so they're not the same thing. Sleet is basically small, round ice pellets that fall. And the cool thing about sleet is that it bounces. Okay, it'll bounce off your windshield when you're at a stoplight in Sanford coming back to Southern Pines from Raleigh. It'll bounce in your hand if you go outside and put your hand out when it's sleeting. And it basically requires a temperature inversion. We will discuss this more in the weather and climate class if any of you guys take that class. Just know this, when it's sleeting, you should not be driving, okay, because it's still ice and nobody can drive on ice. Doesn't matter how good your tires are, or if you have four-wheel drive, all-wheel drive, you shouldn't drive on ice. So it's basically rain droplets that freeze as they fall. Now, freezing rain is very dangerous. It's the most dangerous of all these precipitation types, particularly for driving. Sometimes it's referred to as glaze. And what this happens here is that you have water in a supercooled state. Supercooled fluid, meaning that higher up in the troposphere, you can have water that is below the freezing point and still hasn't frozen to form ice. And it'll fall to the ground in this really cold state. And then if it hits the ground and the ground is freezing or below, it will instantly coat it in a layer of ice. And you absolutely do not want to get out and drive in freezing rain. Just stay home and get ready to lose your power because, tree limbs are going to come down. So, okay, the image on the right is bad enough. That's where, it looks like they're starting to melt a little bit coming out of their freezing rain event. But up on the top left, that's a severe example of freezing rain. I've never personally seen something that bad. Okay, hail. I do want you to know a little something about hail for your last exam, and here's what I want you to know. Hail is going to form in thunderstorms, okay? It takes a thunderstorm to form hail. It probably is going to take a supercell thunderstorm, also known as a severe thunderstorm, to form hail. This is not a wintertime phenomenon. This is a warm weather phenomenon, okay? Late spring, summer, early fall. And the other thing I want you to know about hail, if your thunderstorm is strong enough to produce hail, it could produce tornadoes, and you want to think about a plan of somewhere safe to go if you should get a tornado. Rime, not on your exam, just kind of neat to look at. This is going to happen, of course, in latitudes, and elevations that we don't have here in the coastal plain. It's basically supercooled fog. We're going to skip this slide here. There's nothing on measuring precipitation or wind speed or any of that on our exam, so we're going to skip this slide. Okay, now we're going to do a very brief bit of winds. We don't have much time to talk about winds, but you know what? That's why we have a whole nother class called Weather and Climate. Okay, so air pressure. How about bullets 2 and 3? Okay, so air pressure we've discussed already. It basically refers to the pressure exerted by the weight of the atmosphere above us. And remember that your average air pressure at sea level is 14.7 pounds per square inch. In reality, we have variations in air pressure from place to place all the time. And it's changing pretty often, okay? And that is going to produce wind, okay? So variations in air pressure from place to place are going to cause air to move around. We're going to call that wind, okay? And in case we don't have this on an upcoming slide, I'm going to mention a couple other things that I want you to write down, so I hope you're paying attention. The underlying cause of wind is the unequal heating of Earth's surface. Okay, the underlying cause of wind, why do we have wind on this planet at all? And the answer is because we have unequal heating of Earth's surface. We are heated more at the equator and less at the poles, and that's going to give us differences in air pressure from place to place. So here's the second thing I need you to write down. Hopefully you're paying attention. Air moves from high pressure to low pressure. This is called wind, okay? So wind is the horizontal movement of air molecules from high pressure to low pressure. It's that simple. Air always moves from high pressure to low pressure. It's not going to move at, or it's not going to stop moving around unless you just don't have a pressure gradient at all. Okay, so yes, something that I did mention on the last slide. Let's go ahead and write down bullets 2 and 3. All right, so wind. We all know what wind feels like. We've all experienced wind, and a lot of us have experienced wind associated with various hurricanes and tropical storms that have come through North Carolina. But air always flows from high pressure to low pressure. Okay, and that horizontal movement is called wind. And again, the underlying cause of wind is the fact that our surface is heated unequally, giving us differences in air pressure from place to place. Okay, you don't have to write this down. I'm not going to ask you this on the exam, but we'll briefly discuss it. Okay, so why are some winds stronger than others? It has to do with the pressure gradient, okay? So a steep pressure gradient, which means that you have a big change in air pressure over a given distance, is going to give you stronger winds. And then a shallow pressure gradient, meaning that you have a small change in pressure over a given distance, is going to give you light winds. But this part is not on your exam. Okay, factors affecting wind, not on your exam. We'll briefly discuss it here, but we'll talk about it more if you take the weather and climate class. The Coriolis effect, which has to do with the fact that Earth rotates on its axis, remember, once every 24 hours. And this gives us an apparent deflection in wind direction, okay? And in the northern hemisphere, that deflection is to the right. In the southern hemisphere, that deflection is to the left. If you take weather and climate, we'll talk about it more. And then friction affects wind speed. It actually slows down wind speed. But it's only important near Earth's surface because that's the only place that you have friction. You need some kind of topography to slow down the wind. But again, these factors affecting wind are not on your exam. Here's a nice image of the Coriolis effect, but it's not on your exam. We'll cover it in weather and climate if you take that. So if you want to, you can pause here and look at this. Here we go. Okay. Let's write down bullets 1 and 2. All right, so yes, we've said this before, but I'm glad to see that it actually did make it onto a slide. Okay, so the underlying cause of wind is the unequal heating of Earth's surface, heated more so at the equator, less at the poles. And then, of course, air molecules always move from high pressure to low pressure, and that is wind. Okay, and why does this happen? It's because Earth's atmosphere is attempting to balance this difference in heating, all right? So the atmospheric winds will move warm air from the equator towards the poles, north and south, and then cool air from each pole, north and south, will move towards the equator. And then the fact that Earth rotates causes general circulation. What's not mentioned here, but is true, is that our ocean currents, surface currents in particular, are also trying to correct for this heat imbalance. Okay, so low pressure systems and high pressure systems, mid-latitude cyclones. All right, I take it back. This PowerPoint might be 2 hours and 15 minutes. It might be just as long as the plate tectonics or the volcanoes or the faults and earthquakes. Well, it is what it is. We would normally take probably 4 class periods to cover this, at least 3. Okay, so what is a cyclone? Okay, you might think, I've heard that term before to talk about a hurricane in the Indian Ocean, and the answer is yes, you're right. But a cyclone just means a low pressure center, low pressure system, okay? So you've got low pressure at the center, and in the northern hemisphere, our cyclones, our low pressure centers, are going to rotate counterclockwise, meaning that the winds are blowing counterclockwise. Our cyclones are associated with warm rising air, and they often bring clouds and precipitation. If you didn't get all that written down, then pause and finish. So we also have the opposite of that, which is referred to as an anticyclone, which is a high pressure center. So it's or high pressure system. You've got high pressure at the center, and in the northern hemisphere, these high pressure systems, they're going to rotate clockwise. Another way to describe that is the winds blowing clockwise. So our anticyclones are associated with cooler air that is dense and sinking, and this is associated with fair weather. Okay, those days where the sky is blue and maybe you just have a handful of cumulus clouds and it's a great day for some kind of outdoor event. So this is a nice cross-section drawing here. Let's begin on the left. That's your low pressure center. It's a red L, L for low and red for warm air. Warm rising air, rising why? Because it's warmer and less dense in the air surrounding it. As it rises, it's going to cool by expansion, and then it's going to hit the dew point temperature, and you're going to have condensation, you're going to form clouds, and you might could get some rain from that. And then notice there at the surface that the winds are blowing towards the low, because remember that winds blow from high pressure to low pressure. Those are the purple arrows, and then notice that they are rotating counterclockwise. All right, now let's look at the one on the right, which is everything the opposite of that. It's a anticyclone, okay, high pressure center. H for high pressure. Why is it blue? Because it's cooler air that is more dense and is sinking. Because it's sinking, it's stable, it's not rising. You expect to have clear skies. You're not going to have any kind of significant cloud cover. You're not expected to get rain. Notice the purple arrows are blowing away from the H, okay, because your high pressure is there in the center. Remember that winds blow from high pressure to low pressure. And then notice also that those purple arrows at the surface, they are blowing or rotating in a clockwise fashion. So this is a great way to show the difference between cyclones and anticyclones. Okay, so what we're looking at here is how would we show these things on a weather map, okay? So all they're really showing us here are isobars, which are those black circles, and they are lines connecting points of equal air pressure. They're not showing us any cloud cover or anything like that. That's okay. There in the east, we have a low pressure system, a cyclone, red L. We have the winds, purple arrows blowing towards the L, and they are blowing in a counterclockwise fashion. We expect clouds. They're not showing us. That's okay. They're only showing us part of the picture here. On the left side there, on the western portion of this map, we have a high pressure system, a cyclone. Again, it is a blue H. Notice the purple arrows are moving away from the H. The winds are blowing from the high pressure to lower pressures outside, and the winds are blowing in a clockwise fashion, and we do expect clear skies with the anticyclone. Okay, finally, we are at mid-latitude cyclones. You need to write down the first two bullets here. You can skip the third one there. So mid-latitude cyclones, these are basically low pressure centers, red L, low pressure centers that are constantly forming in North America and then moving from west to east, okay? So mid-latitude, they're called mid-latitude cyclones, just saying that they're forming in middle latitudes. These things are the primary weather producers in the middle latitudes, like all the way from Alaska to Florida, okay? And these things always move east because, again, the United States is in a band of winds known as the westerlies. The winds are blowing from the west to the east. And they usually take 2 to 4 days to move across a particular region. We're going to look at some drawings of this on a weather map. You'll see how big these mid-latitude cyclones are. Okay, so some interesting stuff here. And again, I've got some things in a video lesson already on Canvas about mid-latitude cyclones. I will be going into Canvas and watching what videos I have up there to figure out what, if any, new videos I need to film this week on Wednesday. Okay, so your mid-latitude cyclone, it begins with that low pressure. You got the red L there, okay? You have cloud cover over the low. Why? Because it's low pressure. It's less dense air. It's rising. You're going to form clouds. Notice the red line and the blue line. The red line is a warm front. The blue line is a cold front. So mid-latitude cyclones, you have a warm front on the leading edge. You have a cold front on the trailing edge. Okay, and both of these fronts end up giving you some kind of lifting mechanism, frontal wedging. So we are going to have lifting with the warm front and the cold front. Therefore, we're going to have cloud cover with the warm front and the cold front. We're going to have nimbostratus clouds and rain on the warm front, and we have the chance for cumulonimbus clouds and thunderstorms on the cold front. Here is a satellite image of a mid-latitude cyclone. Look at how many states it covers. And actually, the tail of it goes all the way down into the Gulf of Mexico and Central America. These things are huge, and they are coming across the United States all the time. Okay, jet streams are not on your exam. If you take weather and climate, we'll talk about jet streams. They're basically really high altitude winds, and they're very fast. It's kind of like this fast-moving river of air higher up in the troposphere. Here's an image of the polar jet stream at the top and the subtropical jet stream at the bottom. But again, nothing about the jet streams are going to be on your exam. We will touch on this if you take weather and climate. Local winds. We will not have time for this ever in the earth science class, okay? Be it in class, hybrid, online, COVID, or non-COVID. So we're just going to skip this. We're going to skip this here. If you want to read it, you're certainly welcome to. You can pause and read it. Again, if you take weather and climate, we'll talk about it then. We can skip this. We can skip this. We can skip this. Okay, so we're now going to get into our last section here for this PowerPoint. So I'm hoping we can get it done in, I don't know, half an hour or less. It's going to take forever to save this thing. Okay, so this is all about weather patterns. We're going to touch on the warm front, the cold front, the mid-latitude cyclone, and then we'll talk about tornadoes, thunderstorms, and hurricanes, and then we'll be done. Air masses. I will tell you right now that air masses are going to be extra credits. Okay, in a regular semester, we don't have time for everything because this is not a survey class. And I always make the air masses extra credit on your exam. And certainly during COVID, yeah, it'll be extra credit. Okay, so an air mass is just a big, we don't have to really write anything down yet, even if you are wanting this for extra credit. A big body of air, 1,000 miles across, and it's similar all throughout, similar in moisture content and temperature. So air masses are going to form somewhere other than the United States. Okay, we don't form any of our own air masses because we have too much mixing of air here, but they form all around the United States and move into the United States. And they're going to be classified according to their source region. Okay, if you want to get this for extra credit, then you could write down these 4 bullets here. We're going to go over it very quickly. Air masses are classified according to their source region. They're classified according to latitude. Okay, and latitude will either be polar or tropical. Polar, high latitudes, colder air. Tropical, low latitudes, warmer air. They are also classified according to what is the surface like in that region. Meaning, is it land or sea? So is it continental or maritime? If it's continental, it's forming over the continents, land, and that air is going to be dry. If it's maritime, it's forming over the oceans, and it's going to be a more humid air mass because it's going to be moisture rich because it's forming over water. All right, basic types of air masses. You can write these down if you want to get this for the extra credit. If you're feeling overwhelmed this semester, you can let it go because it's extra credit. All right. Anyway, continental polar, continental tropical, maritime polar, and maritime tropical. There's also a continental Arctic that we don't discuss in this class, but we do discuss in the weather and climate. So continental polar is going to be cold and dry. Continental tropical will be hot and dry and will only affect the desert southwest and only the summer. Maritime polar will be moist and cold. Maritime tropical will be moist and warm. So if you want to have a shot at this for the extra credit, then you may pause here and take a look at this map. This is the best way to visualize. And then we're focusing here on, well, I guess we got all four basic air masses here. So notice maritime polar forming over oceans at higher latitudes, affecting North America. On the west coast very often, on the east coast occasionally. Continental polar coming from, say, Canada, always affecting North America, moving south. Maritime tropical from the Atlantic or the Gulf or the Pacific, forming over water at lower latitudes, always moving into the United States, affecting our weather. And then continental tropical there in the middle. Again, this is only in the warmer months, and it's forming in Central America, moving up into the desert southwest. And we live too far east to ever get affected by the continental tropical air mass. Okay, so again, air masses are going to be extra credit. So just very quickly, we'll go through this. Continental polar air masses are forming in Canada, northern Canada, interior Alaska. And then these things tend to move south down into Canada and the United States. And these things clash with maritime tropical air masses all the time in our mid-latitude cyclones, giving us warm fronts and cold fronts. But the continental polar air mass is very famous in the winter for giving us lake effect snow. Maritime tropical air, warm and moist, coming from the Gulf of Mexico, the Atlantic, for affecting us east of the Rockies, but on the west coast they're getting affected by maritime tropical air masses coming from the Pacific, and these things are always moving into the United States, and they're bringing moist, warm air that is potentially unstable. And this brings a lot of precipitation to the United States east of the Rocky Mountains. Continental tropical, again, not affecting us in North Carolina. Hot and dry, forming in Mexico in the desert southwest, and then affecting the desert southwest, basically, of the United States. In the maritime polar, if we all lived in Seattle, we'd be hearing about maritime polar air all the time. So bringing a lot of precipitation to the western U.S., especially where you have mountains, which is all the west coast of the U.S. You've got various mountain ranges. And then occasionally it will affect the northeast U.S. in the form of a nor'easter, bringing cold winds, perhaps rain or snow. And this is generally a wintertime phenomenon. And I think it's pretty rare that we get affected by the nor'easter this far south. But occasionally it can happen. Okay, fronts. Let's write down all three bullets here. Okay, so what is a front? It's just a boundary. It's a boundary that's going to separate air masses of different densities, okay? So if you have warmer, less dense air, it's going to be forced aloft. When you've got colder, more dense air in place or moving into your area, it's going to act as a wedge, forcing warmer, less dense air it comes in contact with upwards. Okay, so front is a boundary. We're going to have, well, there's more than two types of fronts. For this class, we're just going to discuss the warm front and the cold front. If you take the weather and climate, we'll also talk about stalled fronts and occluded fronts and dry lines. Okay, so the warm fronts. Honestly, let's write down every bullet here. So you may have to pause this. A warm front means that warmer air is moving into your area, warmer than what you have presently here. Warm air replacing cooler air. On your weather map, it's a red line with semicircles. As your warm front's moving in, you're going to start to see thicker clouds build, but you do not expect thunderstorms with a warm front. You do expect rain, but not thunderstorms. The warm fronts move pretty slow, and you can expect light to moderate precipitation and nimbostratus clouds along the warm front. And then as that boundary moves on out, then you'll have warm air behind it. But then what should you expect to be moving along next into your area? A cold front, of course. So we'll move on. Here's a nice cross-section drawing of a warm front. See where it says moderate precipitation. Pretend that that's where UNCP is. So we have a cooler air mass over top of us, but we have warmer air moving in. You see the front, the boundary there to the left. That warm air is forced up and over the cold air. Remember, this is frontal wedging. That cold air, or the cold air, is a wedge of cold air acting as an invisible mountain range. And that warm air is pushed up and over it, and you're going to hit the dew point temperature with cooling, and you're going to form clouds, nimbostratus clouds, and rain. Okay, the cold front. We should write down every bullet here. So again, you may need a pause. A cold front means that cooler air is moving into your area. It's cooler or colder than what you have in place right now. Cooler air replacing warm air. On your weather map, it's a blue line with triangles. The cold front moves faster than the warm front. It moves about 50% faster than the warm front. Means eventually the cold front catches up to the warm front and gives you an occluded front. We will not worry about the occluded front for our semester. Now, that last bullet there is important. So the associated weather with a cold front has the potential to be violent, okay? It could bring some strong thunderstorms, and it could give you some high-intensity rainfall, perhaps hail, perhaps tornadoes. Hail and tornadoes more likely in the warmer months of the year. But the good thing about the cold front is that it moves relatively quickly. So whatever violent weather that you might, and it doesn't always bring it. In the warmer months, you're more likely to get the violent weather with the cold front. At the very least, it's not going to last real long. It'll move out of your area pretty quickly. Okay, so what does a cold front look like, to the observer on the ground as it moving in? A wall of dark clouds. So you expect to get thunderstorms, cumulonimbus clouds, heavy rain, possibly hail, occasionally tornadoes, and then the bad weather will move out quickly because the cold front moves fast. And what are you going to get behind it? Cold air, subsiding air, clearing conditions, and yeah, basically clearing skies. Here's a nice cross-section drawing showing the cold front moving in. So let's say that there to the east, where it's just yellow, that is where Pembroke is. And you've got warm air over top of you right now, but a cold front's moving in. And it's got a very steep slope to it, which is going to allow it to scoop up a lot of warm, moist air that has probably originated from the Gulf of Mexico. And you're going to get a lot of fast lifting and cooling and condensation and releasing latent heat energy with the condensation that builds these really tall, thick cumulonimbus clouds, bringing you a thunderstorm. Okay, now yay, we're getting close. Thunderstorms. Everybody's been through thunderstorms. We know what they're like. Cumulonimbus cloud, heavy rainfall. You could get some flash flooding, lightning and thunder. Sometimes you get hail. Again, if you are in a thunderstorm and you've got hail, that is your indication that that is a violent thunderstorm. And you should get to some kind of safety because hail is not good and it can smash windshields of cars. Also, if there's hail, it means that that storm is capable of producing tornadoes, and you really want to be aware. Okay, so thunderstorms are most frequent in Florida and the eastern Gulf Coast. Kind of makes sense. Those are areas where you're going to have warm, well, they're warmer areas than, further north, but important. These are areas that are right there on the Gulf of Mexico, meaning that they're right there getting maritime tropical air moving in all the time. That will then clash with continental polar air moving down from Canada, giving you cold fronts and potential thunderstorms. Okay, you don't have to write any of this down. I'm not going to ask you to know what thunderstorms require, but we will discuss it. Okay, so they require warm, moist air. Okay, and that air needs to be unstable, meaning that there's some kind of lifting mechanism. It could simply be that the air is less dense, warmer and less dense than the air around it. And basically, like say for your typical afternoon thunderstorm, evening thunderstorm in the warm months, you need high surface temperatures. You need a lot of daytime heating. Okay, so thunderstorms, let's write down the first two bullets here. Why not? So these, of course, are your typical, pop-up thunderstorms, afternoon thunderstorms. We might refer to them as air mass thunderstorms that you expect to get in the warmer months. So most common in the afternoon and early evening. Kind of makes sense because remember there's a lag time throughout the day for that terrestrial re-radiation, and you hit the higher temperatures in the afternoon. Okay, so they're most common in the afternoon and early evening. Kind of rare to get a thunderstorm in the morning. It's not impossible, but it's rare. All right, so what else is associated with thunderstorms? Surges of warm air that are rising upwards. We could refer to this as updrafts. And again, as this air is rising, it's cooling, you have condensation forming droplets, forming clouds, and that's releasing heat energy to that air mass so that it can keep rising further and condensing more, building that tall cumulonimbus cloud. And then eventually you're going to end up with heavy rain and possibly hail. All right, so let's write these down because it's important. So just some characteristics of typical thunderstorms. You're going to have updrafts and downdrafts, and they can be violent, meaning that the air is, warm air moving upwards very quickly, colder air from higher within that cloud moving down very quickly. Downdrafts especially are very hazardous for airplane travel, particularly when you're trying to take off or land. Thunderstorms, you expect heavy precipitation, could be some flash flooding, gusting wind, dangerous lightning and thunder, and of course possibly hail. So here's a map just showing the average number of days with thunderstorms in various states. Again, Central Florida is the winner, anywhere from 80 to 100 days of the year with a thunderstorm. So stages in the development of thunderstorms, not on your exam, not in the earth science class, so we will skip this. Okay, tornadoes. All right. Yeah, let's write down every bullet here. So we are getting close to the end of this presentation and close to the end of our semester. Tornadoes and then hurricanes, and then that's it, guys. It's going to take this a good hour and a half to save. Okay, so tornadoes are local storms, meaning they're not, they're only so big. Short duration, meaning that they tend to not last real long. Although there was an EF3 that was a mile across and stayed on the ground for 63 miles, a very long time period there, that hit North Carolina back in April of 2011. Relatively short duration, we'll say. Rotating column of air between the base of a cumulonimbus cloud and the ground. And you have intense low pressure in the center. You have basically a very large pressure gradient between the center of that tornado and outside, which is what causes your high winds. And the worst case scenario, your EF5 tornadoes, you can get wind speeds actually of up to 305 miles per hour. So some images of tornadoes. All right. Yes, we need to write this down. I'm going to tweak that third bullet there, so please pay close attention. I'm going to want you to know when is tornado season. I'm putting season in quotes because it's not an actual season. That's the first bullet there. They are more likely to occur April through June. Exam question. You actually could skip the second bullet there. I'm not going to ask you to know how many per year, but this is actually pretty old material here. Maybe almost, gosh, more than 10 years old. U.S. averaging 770 per year. I feel like that number's probably gone up. They are associated with supercell thunderstorms, okay? Let's write that down. Supercell thunderstorms, not just any thunderstorms. And that goes along with bullet number 4. Your tornadoes are generally, oh, you do have supercell thunderstorms on there, sorry, okay. Tornadoes are likely to occur along cold fronts. Why? Because cold fronts, remember, can bring you violent weather. And sometimes with your cold fronts, you get the really big, severe thunderstorms that we refer to as supercell thunderstorms, all right? So, supercell thunderstorms are not going to occur on the warm front, okay? And your supercell thunderstorms along the cold front are the ones that are most likely to form tornadoes. So your average afternoon thunderstorm on a hot day, what we might refer to as an air mass thunderstorm, is not likely to form a tornado. Thank goodness for that. Okay, so this is something I like to show in class, and we'll certainly try to do that this coming week. And I think this might even be in one of the, maybe this is in a video lesson. We'll have to see. And there may be some video lessons from the weather and climate class that if I haven't already put a link for them into the earth science class, I'm going to do so this weekend. Anyway, so going way back to 2006, 2007, Tropical Storm Hermine hit Texas, and Dr. Greg Forbes did a little demonstration and described tornado formation as it occurred due to that tropical storm. So tornadoes can form in our tropical storms and hurricanes as well, not just along the cold fronts. But what you need wind shear to form a tornado, okay? So in the case of Hermine, you had winds at the surface that were going in a certain direction, like let's say moving to the east, but then you had winds above that at a higher altitude that were moving north. So you had winds that were perpendicular to each other. Okay, that's one type of wind shear. And what happens here is that if you have wind shear, you can get this horizontal rotating column of air. And that might sound scary because it's a rotating column of air, but if it's horizontal on the ground, it's not that bad. But if an updraft in your thunderstorm picks that horizontal column of air up and makes it vertical, then it's a tornado, and then it's very dangerous. Okay, so again, so the wind shear creates a rotating horizontal column of air, like rolling a pencil. And then if it's not that bad, if it's, you know, horizontal on the ground surface. But remember that your thunderstorms, particularly supercell thunderstorms, are going to have violent updrafts and downdrafts. So if an updraft then lifts this rotating horizontal column of air up into a vertical position, then it's now a tornado, and it's very dangerous. Okay, so no, you do not have to know any. We're going to talk about spring 2011 tornado season and all the outbreaks. Here's what you need to know. 2011 was probably the worst tornado season in all of our record keeping. Okay, that's all you need to know. What was the worst year for tornado season in the United States? And that answer is 2011. Okay, other than that, you don't have to write this down, but we're going to go through these because we usually do this in class and we won't have time. So April 14th to the 16th, 2011, more than 155 outbreaks across 16 states, including North Carolina. In that 3-day period, guys, and I remember this, I was teaching here but living in Wilmington, and I was just constantly watching. A lot of these were happening over the weekend. I remember being at home in Wilmington watching this on the Weather Channel, just nonstop. We had at least 30 tornadoes in North Carolina in that 3-day period, including that one I mentioned earlier, an EF3. It was a mile wide, which is pretty big for a tornado, but we're seeing more of that in recent years. And it stayed on the ground for 63 miles. It hit Raleigh, Sanford, Esquivel, Fayetteville, and Dunn. This image made national news. This was the Sanford lows. Everybody lived through this. I remember seeing that on the news. Just some images here of tornado damage. April 22nd, 2011, St. Louis, Missouri was hit pretty bad. Here is a before and after image of a neighborhood. April 25th to the 28th, 2011, estimated 305 tornadoes. That's a lot of tornadoes in 3 days. hit from Texas to New York. Okay, so let me ask you guys, is New York used to getting tornadoes? No, but they do occasionally, especially as time goes on. This was a horribly bad tornado outbreak. Okay, 21 were F3s. Those are deadly. 12 were F4s. Those are even more deadly. And 3 were F5s, which are the most deadly, and can have wind speeds over 200 miles an hour. So nearly 350 fatalities in 3 days, mostly in Alabama, and Tuscaloosa was very hard hit. Here's a really big tornado in Tuscaloosa from that outbreak. Here's some damage in what appears to be some kind of apartment building or townhouses maybe in Tuscaloosa. They had to shut down the university for a while. Okay, May 22nd, Joplin, Missouri got hit. It was only one tornado, but it was an EF5, the worst. And this one tornado killed over 100 people. So one of the country music stars did some kind of benefit concert. So the images from Joplin, Missouri, everything is just destroyed. So the trees are clipped. Every building is knocked over. It kind of looks like a devastating tsunami hit. Okay, so this is our old school statistics for tornadoes. They used to have an average diameter between 500 and 2,000 feet. Well, we are seeing, more and more that some of them are a mile across, which is 5,280 feet. They used to cut a path of 6 miles. They seem to be staying on the ground longer. Again, that one that hit Raleigh stayed on the ground for 63 miles, 10 times the old average. They are measured by the Fujita scale. Here is the Fujita scale. It goes from EF0 to EF5. Yes, there's a 0, okay, but still, a 0 has wind speeds between 40 and 73 miles an hour. So it's not nothing. But if you're going to have a tornado in your area, you hope that it's an EF0. So this is kind of old. Again, this goes back to probably prior to 2008, I would say. Annual tornado incident per 1,000 square miles. Can you find Tornado Alley on this map? Of course you can. It's right there in the middle, where you've got like 9, 8, and 7, and yeah, 9, 8, and 7 for maybe 5, I guess, in the lighter orange for the number of tornadoes per year per 1,000 square miles. There's also something called Dixie Alley, okay? Look at Florida. They get some decent tornadoes, and then Dixie Alley actually does extend into North Carolina, unfortunately. And then look at that graph over on the left, okay? Remember we said that tornado season is April through June. That's April, May, and June, and you see that on that graph. Okay, I'm going to want you to know the difference between the tornado watch and the tornado warning, okay? So I would write down the purple bullet and the first 2 red bullets, all right? Tornado watch is going to be issued when the conditions are such that tornadoes could form, so they're possible, okay? When the conditions are favorable. So if you have supercell thunderstorms in your area, they're going to issue a watch. If you have a tropical storm or hurricane hitting your area, they're going to issue a watch. So how is a warning different? We're going to see that. So the tornado warning, they won't issue a warning unless they know that one has formed, okay? So you could just write down that purple bullet there would be fine. So either somebody sees it on the ground and reports it, or it's indicated by Doppler weather radar. And it'll have this little hook to it, kind of like an eagle's beak, okay? And they refer to that as a hook echo or a bow echo. So even if nobody sees it yet, because it's on the outskirts of town, we're going to know that it's there because of that hook echo. So that's the difference between watch and warning. When it's a watch, be aware and keep an eye on things and don't go taking a nap. When it's a warning, it means actually get to safety right now. So we'll look at just a handful of older images, as in prior to 2011. Okay, so sometimes they call this missile damage. Notice that there's a flimsy piece of wood here now stuck into concrete on the side of a building, okay? Um, they don't give a tornado a number. They don't assign it a number until after it's over. So, do we have instruments nearby to try to capture wind speeds? Not necessarily. And if we did, those instruments might just get destroyed. So when the tornado has moved out, then experts from the National Weather Service will come in and look at the damage. And we've done, research, and we know what kind of wind speeds it takes to take a flimsy piece of wood and stick it into concrete. Okay, hurricanes. This is officially our last topic here. So hopefully this can be no more than 2 hours and 20 minutes for this PowerPoint. Still take an hour and a half to save. So let's write down the last 4 bullets. Okay, the last 4 bullets are what I want you to write down. So these are the most violent storms on Earth, the biggest storms on Earth. The wind speed with hurricane is probably not as high as you get with tornadoes, but they're so big and they move slow and they cause so much damage. Therefore, we're going to call them the most violent storms on Earth. So you need to reach at least 74 miles per hour to go from tropical storm status into Category 1 hurricane status. So in the Northern Hemisphere, your hurricane is basically just a big, scary, deadly, violent, low pressure cyclone. Therefore, it's going to rotate counterclockwise in the Northern Hemisphere as every other cyclone will do. They don't form just anywhere. They don't form right at the equator because, well, there's not strong winds right at the equator, and the Coriolis effect is pretty much 0 at the equator. So they're going to form between the latitudes of 5 and 20 degrees, and this is north and south of the equator. That last bullet there is especially important, definitely an exam question, definitely short answer. Hurricane season in the Atlantic is June 1st to November 30th. We are still in hurricane season. This is November 2020, and Hurricane Eta, which is our 5th or 6th storm from the Greek alphabet, it has now left Central America. It did a bunch of damage. It's out there in the Caribbean, moving towards the Gulf, and it's going to move over Cuba, and it's going to hit Florida. And then we'll have to see what else it's going to do. Okay, so for extra credit, you might write down those first 3 bullets there. All right, what are they called in the Western Pacific when they're going to hit, say, Japan or Southeast Asia? They call them typhoons. And what are they called in the Indian Ocean when they're going to hit, say, India or Indonesia? They call them cyclones. I'm going to want you to know that the eye wall is where you have the fastest wind speeds and the most rain. And that may or may not be listed on the next slide. So let me mention that again. Okay, the worst part of the storm is the eye wall. It's basically a big wall of cumulonimbus clouds. It's really basically just a bunch of organized thunderstorms. And you're going to have the greatest wind speed and the heaviest rain in the eye wall. Here's a picture of the eye wall. You see the airplane wing there. So these are the hurricane hunters. These are brave people. I think it's a combination of Air Force pilots and people from the, meteorologists, National Weather Service, and they fly into the hurricanes. Anyway, so there's your eye wall, a big wall of cumulonimbus clouds. What happens in the eye? Everybody know? It's calm, and the wind stops, and the rain stops, and it's hot, and it's humid, and you don't have any AC because the power's out. Here you go. Let's write these down. Here it is officially. So the eye wall. This is where you have your greatest wind speeds. This is where you have your heaviest rainfall. It is a wall of cumulonimbus clouds. The eye wall is the worst part of the storm to be in. You may need to pause here to get it written down. What happens at the eye? It's calm. Okay? It's calm, the wind dies down, and the precipitation stops. It's calm at the very center in the eye. Of course, in the eye, if you're in the eye of the hurricane, it means that you've already lived through one eye wall. the eye wall on one side, and it doesn't mean that everything's just okay because the storm is moving, and it means that you've got the eye wall from the other side still to move over you. Here's an image of a hurricane hitting the Gulf Coast. It's possible that this is Katrina, or it could be, what was the one after Katrina? Oh, I'm having a brain fart, and I can't remember the one that was right after Katrina. Here's a cross section of a hurricane. Okay, so interesting things here that you don't have to write down. The wind speeds can be greater than 155 miles per hour. Again, the winds associated with a hurricane are not as strong as with a tornado, but the hurricane is much larger and moves slower and can potentially cause more damage and heartache. They may generate 50-foot waves at sea. Something interesting I like to bring up in class, which we won't have time for this time, is that the Navy, and I know because John, my super ex, he was ex-Navy when I met him, and when he was stationed in Virginia Beach, well, the Norfolk Navy base, when hurricanes were coming in, everybody associated with that ship, you left, family, pets, your home, your stuff, and you got on the ship and you go out to sea because the Navy ships are made to take 50-foot waves. But if you leave them in port, they're just going to tear everything up and they might end up perched kind of on land. And they tend to form in all tropical waters except the South Atlantic and eastern South Pacific. But I know of at least one anomaly where we had one form in the South Atlantic. That was many years ago, maybe in the late 90s, I want to say. Okay, so let's write down the last two bullets here, the ones that are in red. So it will begin as a tropical depression, but it won't be elevated to the status of tropical storm until the winds hit 39 miles an hour. Okay, so a tropical depression is basically a low pressure system out there over the ocean. And it's got low pressure at the center. That's why it's called depression and forming in the tropics. And as it starts to pick up steam and the winds hit 39 miles an hour, then they're going to call it tropical storm. That's when it gets a name. It doesn't have to wait till hurricane to get a name. And it will remain a tropical storm unless the wind speeds hit 74 miles an hour. And then at that point, it becomes Category 1 hurricane. So, you don't have to write this down, but when do they start to tear apart? And we know this from, living in a coastal area. They diminish in intensity when either they move over cooler ocean water, which happens to the ones that don't make landfall and just go north in the Atlantic, or they will start to dissipate when they move over land and make landfall. But we know from any number of storms, including Floyd and Matthew and Florence, that just because they make landfall, it does not mean you're out of the woods. They can last for many days, cause catastrophic flooding, have some high winds, and take quite a while to break apart. Okay, so things I might want you to know. I'm going to want you to know that and I don't think it's really worded here like this, but I'm going to mention it, and I hope you're paying attention. Really, the most deadly aspect of the hurricane is the storm surge, which is basically a dome of water, okay, and it's pretty wide, 40 to 50 miles across, and basically it's the ocean pushing up onto land, okay, and this happens where the hurricane makes landfall, okay, so the storm surge is the most dangerous aspect of the storm. This is why they will tend to evacuate beaches and barrier islands pretty quickly. But wind damage is also an issue. And of course, inland flooding, unfortunately. When it makes landfall, those of us not living right at the coast can still be in trouble because it can stall and then cause a bunch of rain. And we saw that in Floyd back in '99. We saw that in Matthew in 2016. We saw it in Florence in 2018. So, here's an image from Floyd in '99. So the Saffir-Simpson scale is going to rank the intensity of our hurricanes. This is not on your exam. And here's the Saffir-Simpson scale. And this is quite terrifying because what I want you to look at is the wind speed and the storm surge in feet, okay? Even a 3, storm surge of 9 to 12 feet. Think about barrier islands. Nowhere on that barrier island do you have it more than maybe 5 to 7 feet above sea level. Okay, so the storm surge can completely roll over barrier islands and coastal areas. And you get to category 5, and that storm surge is 18 feet.